So we can quickly do this example. This is the same which we were doing before. So I'm gonna just read it one more time and then we'll try to finish this example, and we'll also try to do example 4.2. So we know that this is a circular cylinders and we had gear fixed to the rigid wall. So this is the shaft 1, this is shaft 2. Shaft 1 was made up of brass, this is made up of aluminum. So we know the material properties for the brass. So the material property for brass was 200 gigapascal was the Young modulus of elasticity. Poisson ratio was 0.34. For aluminium, the modulus of elasticity was 70 gigapascals and the Poisson ratio was 0.33. We already know the distances. This was 10 centimeter. This was 8 centimeter. The diameter was 1 centimeter. The diameter for shaft 2 was 1.5 centimeter. The diameter for the gear was 40 centimeter and the diameter for gear 2 was also 30 centimeter. So the first question was calculate torque, which we have already done, but I'm gonna just quickly do in front of you guys. So this, let's just draw a free body diagram. So this is a free body diagram. I'm going to convert everything into torque because we are interested in torque. So I'm just going to talk about torque. We know we have a reaction torque here, which is T of X. And then we also have the torque here. So I'm going to convert the loads, these loads into torque. So we know the load, we can multiply with the moment arm, and then we can convert this into torque. So let's calculate torque at A. So we know the force. Force was 800 Newton. This is 800 Newton. This force was 1200 Newton, right? So if you multiply force with the moment arm, which is 40 by 2 into 100, you're going to get torque value. And the torque value you're going to get is 160 Newton meter. Similarly, you can calculate torque at B. The load was 1200. Moment arm is 30 by 2. And you have to multiply by 100. You can calculate the value of torque in this way, which is going to be 180 Newton meter. So I'm going to draw a free body diagram once again here so that it's easy for you guys. So this is, so that's the torque, T of A, which is 160 Newton meter. And you have another torque here, which is 180 Newton meter. So last time we used all the equilibrium equations to calculate the torque, but that's an easy way. You can just convert everything into torque and then you can do the summation of, so either you can do summation of torque is equal to 0, or you can say summation of moment along x-axis is equal to 0. This is x-axis, this is y-axis, this is the axis, it's the same thing. So if you do summation of moment along x-axis, you're going to get torque at x-axis plus T of A minus T of B is equal to 0, which is T of X plus 160 minus 180 is equal to 0. So torque, you can get it this way, which is 20 Newton meter. So that was part A, like calculate the torque. So we have converted all the loads into torques, and then we have done summation of moment along x-axis is equal to 0. So you have these three moments which are acting along x-axis. So our value came out to be 20 Newton meter. which is exactly what we have calculated before. Now the second part is we have to calculate angle of twist at gear A and gear B. So basically we have to calculate angle of twist at this point and we have to calculate angle of twist at this point. So you can imagine how a rotation would be. So there is one torque which is acting at this location and then there is another torque which is acting at the gear B. So if you try to imagine how the angle of twist would be, you have a straight line, and when this gear is going to try to twist, so the straight line will go something like this from here to here. And then you have at gear B, you have twisting on the other direction. So from here, this line would go up against somewhere. So this is the angle of twist here. So we have to calculate angle of twist at gear A and angle of twist at gear B. So the formula for angle of twist is TL over GJ. So here you have a torque. So because of this torque, this line will go down, and if you draw a circle, before the line was here, now it's gonna go here. So this is the angle of twist. And there is another torque at TB. So the angle of twist is already some angle of twist, and from here it's gonna start another angle of twist from here. So I'm gonna write the equations for the angle of twist at point A and at point B, and you guys can let me know if it makes sense or not. So the angle of twist at point A, so you have angle of twist 0 at the fixed location because it's fixed support, it's not going to have angle of twist, but there's going to be some angle of twist at gear A, which is denoted by phi A. Then there is another angle of twist at gear B, which is denoted by phi B. So angle of twist at A would be equal to TL over GJ, but it's like, because we are talking about shaft 1, so we have torque 1, length 1, shear modulus of elasticity 1, and the polar moment of inertia for the shaft 1. And for the angle of twist at B would be equal to angle of twist A plus T2 L2 over G2 J2. So these are the equations for calculating angle of twist at point A and angle of twist at point B. The reason why we have to add angle of twist of A is because you had no angle of twist and then you had some angle of twist, right? And then it's gonna add the already angle of twist you have. The next angle of twist is gonna be added to the already angle of twist we have. So that's why we have this equation. So let's try to calculate all these variables. Once we'll have all these variables, we can calculate the angle of twist. So we already know what length is. Let me draw a free body diagram again. So we have a torque here, we have a torque here. We also have a reaction torque. The value of this torque was 160 Newton meter, which is TA. TB is equal to 180 Newton meter. And this is Tx, which was 20 Newton meter. This is L1, right? This is L2. So L1 was 10 centimeter and L2 was 8 centimeter. So we know L1 is 10 centimeter, which is 0.1 meter, and L2 is 8 centimeter, which is 0.08 meter. We have also calculated J1 and G1 in our last class. So I'm going to just write the equations for you. G1 was G. If you want to calculate G, the equation to calculate shear modulus of elasticity is Young modulus of elasticity divided by 2 into 1 plus Poisson ratio. And the value for J is pi by 2 R4. And last time we have calculated G1, J1, uh, G2, J2. So I'm just going to write it down here. G1 was 37.3 gigapascals. J1 was 9.81 into 10 raised to the power minus 10 meter 4. G2 was 26.3 megapascals. So it was gigapascals. Gigapascals. J2 was 4.97 into 10 raised to the power minus 9 meter 4. This is what we calculated in the last lecture. So we already have everything. We have L1, G1, J1, we have L2, G2, J2. All we need is to calculate these torque values. So once we can calculate these torque values, then we can calculate the angle of twist. So how to calculate the T1 and T2? So these T1 and T2 are basically the internal loads. So remember, whenever we have to calculate shear stresses, shear strains, or stresses or strains, or angle of twist, or elongation, we need to know the internal loads. So here also for angle of twist, we need to calculate the internal torques. And once we can calculate the internal torques, we can feed in those values, and then we can calculate the angle of twist. So how to calculate the internal torques? We can calculate the internal torques by making cuts, right? So if you cut a section in a shaft 1, you can expose the internal torques in the shaft 1. If you cut a section in the shaft 2, then you're going to be able to expose the internal torques in the shaft 2. And once we can calculate those torques, then we can put the values in the equation of angle of twist, and we can calculate the angle of twist. So let's try. So I'm going to draw free body diagram, and then I will also try to cut a section, and we'll see. So I'm going to draw a free body diagram again for the whole section without the cuts. So this is torque, which is 160 Newton meter. This is torque, which is 180 Newton meter. We have already calculated the reaction torque, which is 20 Newton meter. Now we need to expose the internal torques. So we're going to make two cuts to expose the internal torques. So we can also draw a free body diagram for the cuts as well. So now we have exposed the internal torques. Now we're going to use equilibrium equations, and then we can calculate the T1 and T2. And once we have the T1 and T2, we have all the other variables, we can calculate the angle of twist. So I'm going to do summation of moment along x-axis is equal to 0, or summation of torque is equal to 0. This is x-axis, this is y-axis, this is z-axis. So if I use this part, I'm gonna get T of x plus T1 is equal to 0. So T1 is equal to negative Tx, so it's negative 20 Newton meter. So I've calculated T1. We can use this part of the section, and we can use the equilibrium equations. It's gonna give us negative T2, negative TB is equal to 0. So T2 would be equal to negative TB, which is negative 180 Newton meter. So now we have calculated the internal torques as well. We have all the things we needed. Now we can input all these values in the equation, and we can calculate the angle of twist. So what was the equation for angle of twist at gear A? It was T1 L1 over G1 J1. What was the equation for angle of twist at point B, at gear B? It was the angle of twist we already got from the starting point plus the additional angle of twist we'll get from additional torque values. So angle of twist at A would be equal to torque 1, which is negative 20 Newton meter, length which is 0.1 meter, G1 is 37.3 gigapascal. Giga is 10 raised to the power 9. Pascal is Newton per meter square. The value of J1 was 9.81 into 10 raised to the power minus 10 meter 4. So these 2 meters gonna cancel out. You're gonna get meter squared. This meter squared is gonna cancel out with these 2 meters. This Newton is gonna cancel out with this Newton. So we got angle of twist as negative 0.0546 radians. So now we can use this equation. So angle phi would be negative 0.0546 plus, what was the value for the torque 2? The value for torque 2 was negative 180 Newton meter, and the length was 0.08. G2 was 26.3 gigapascals, which is 10 raised to the power 9. You had J2, which was 4.97 into 10 raised to the power minus 9. So you can calculate angle of twist at gear B by solving these values. So it's going to be 0.0546 minus 0.097, because this is minus, so it's going to end up getting the minus value. So your angle of twist at point B would be negative 0.152 radians. The third part is calculate shear stress at x is equal to L1 plus L2 by 2. At this distance, we have to calculate the shear stress. We know the formula for the shear stress is TR over J. All we have to figure out is which torque to use for the shear stress, which radius to use for this type of shear stress at a distance L1 plus L2 by 2, and what would be the polar moment of inertia at this point. So we are talking about this point. So we have to calculate shear stress at this location. So basically we have to calculate shear stress in the shaft 2. So in this case, I would imagine the shear stress, we are talking about torque 2 because this is shaft 2. We are talking about radius 2, and we are also talking about J2. So we know for this shaft, our D2 was 1.5 centimeter. And torque we have already calculated inside, which is how much? Which is negative 180 Newton meter. So we're going to use these values and we can calculate the shear stress at a location which is shown here. So the shear stress at this point would be negative 180 into radius. Radius is 1.5 by 2. Half the diameter is radius. And the J2 was the polar moment of inertia in the shaft 2, which was 4.97 into 10 raised to the power minus 9. And we also have to multiply by 100 because we have to convert it into a meter. So this would be equal to 271 into 10 raised to the power 6 Newton meter. Which Newton meter, yeah. Yeah, that's about it. 271 into 10 raised to the power 6 Newton meter. That's the answer for shear stress. So in the exam, I will give you guys the formula sheet also, but I will not let you know which value is which. For example, it was like the formulas will be given in this way, like the shear stress is TR over J, the angle of twist is TL over GJ, force is stress is force per unit area. So I will just give you, so these things will be written on the exam. But of course, I mean, you have to figure out this is shear stress, this is polar moment of inertia, this is force, this is stress. But I will give you the equations. But I will not let you know which symbol indicates What parameter? Yes. Yeah, yes, yeah, I can either I will give you the value of G or I will give you the formula for G, which is E by 2 into 1 plus Poisson ratio. And I will give you the value of modulus of elasticity E and Poisson ratio V. So all the values will be given. For the value of shear stress. For the shear stress. No, yeah. Right. Absolutely, absolutely. Shear stress should be, you're right, Newton per meter square. This is what you're saying, right? Yeah, absolutely. Right. Yeah, thank you. So it should be mega, it's 10 to the 6, right? Megapascals. Yeah, stresses are in pascals, Newton per meter square. That's right, that's correct. So if this is clear, we can move to example 4.2. And also we can see we were able to calculate the reactions by just using summation of forces. So this is a determinate system. This is not an indeterminate system. So this is example 4.2, which is kind of very similar to example 4.1. There are some minor differences, but these differences make a big deal because now you may see the system is now not a determinate system, but we'll see. So this is almost the same example with minor differences. So now it's fixed between the two rigid walls. So if you draw a free body diagram, now it's fixed at the both ends, this system. So the first shaft is made up of brass. This is shaft 1, this is shaft 2. Same, it is made up of brass, so modulus of elasticity we know for the brass is how much? 100 gigapascals. The Poisson ratio we already know, 0.34. This is aluminium, so the modulus of elasticity is 70 gigapascal. Poisson ratio was 0.33. We know these values. The length is also same, 10 centimeter. This length is also same, which is 8 centimeter. Uh, the diameters are also same. The D1 is 1 centimeter. D2 is 1.5 centimeter. And this is gear A. So the gear A has diameter 40 centimeter, which is also the same. The load is 800 Newton. So before we had two gears, now we have one gear and the load is 800 Newton. And now before we had fixed support at one end and now we have the fixed support at both the ends. So we can convert this load into a torque. So in this case, the torque would be equal to 800 into the moment arm. And moment arm is half of the diameter and we have to convert it into a meter. So I will divide by 100. So the moment will come out to be 160 Newton meter. And this is the direction of the torque. So let's say this is point A, this is point B, this is point C. So the torque is 160 Newton meter. And as a result, we'll have reaction torques. This is TB, this is TC. So now you can see this is now not a determinate system, this is an indeterminate system because if you try to do summation of moment along x-axis is equal to 0, you have one equation, but you have two unknowns. So if you try to use equilibrium equations when you try to solve this system, you will not be able to solve this system because it's an indeterminate system. So we have to use another equation. So we have to use some compatibility equation. And now in this case, we don't have deformation, we have angle of twist. So we can try to make some relationship of angle of twist, and we can try to figure out like which angle of twist for the shaft 1 is same with the shaft 2. And in this way, we can like come up with a new equation using the material properties, which is called a compatibility equation. So we know this is 0.1 meter distance, and this is 0.08 meter. We also know at this point this is a fixed support, so the angle of twist is 0 because a fixed support cannot rotate, so angle of twist is 0. This is also a fixed support, so the angle of twist here is also 0. And here the angle of twist is some value. We can calculate the angle of twist here using the formula TL over GJ. So you can imagine here you have no angle of twist, here you have some angle of twist, and here also you have no angle of twist, because if it's a fixed support, you're gonna get no rotations, you're gonna get uh, reaction forces also and moment reactions also. So no angle of twist on the fixed support, some angle of twist at the gear A. So we can see from here for the shaft 1, the angle of twist is the same as the angle of twist for the shaft B. So the angle of twist are same basically. So we know angle of twist, this is same for the shaft 1 and shaft B. So I can write, and you can let me know if I'm wrong. So if this is B, this is C, and this is A. So from angle of twist from B to A, there was no angle of twist, and now we have some angle of twist at A is equal to some angle of twist at A and negative. So from here to here, the angle of twist was increasing, and we had some value, and we can call it BA. And then there is some angle of twist, and then there is no angle of twist. So angle of twist is same at this location. So the angle of twist for BA would be equal to angle of twist from AC, but negative in direction. Or you can also write it this way. Angle of twist from B to A plus angle of twist from A to C is equal to 0. So you have some angle of twist, and then that angle of twist again reduced to 0. So the sum of angle of twist is 0. So these are the, this is called compatibility equation. And since we are seeing rotations, so that's how we can calculate the compatibility equation through the uh, angle of twist or the rotation. So this is a compatibility equation. So what is the question? So the question is calculate TB and TC. That's the question. And since it's an indeterminate system, so it would be a little bit harder to calculate the reactions directly. So we use compatibility equations and stuff. And this is a super important example because something similar is going to be a part of exam. So you can go back also later and try to solve this. And we'll also do one more example next time to make it more clear. So let's use the values. Let's use this equation, angle of twist. So we know angle of twist is TL over GJ. So I'm going to use this compatibility equation and I will put the values. So this is T1 L1 over G1 J1 is equal to negative T2 L2 over G2 J2. as we have done in the last example. We already know the values for L1, G1, J1, so we can put the values and we can see uh, what are the results. So T1 into length was 0.1, 0.1. G1 was 37.3 into 10 raised to the power 9. J1 was 9.817 into 10 raised to the power minus 9 is equal to T2 into length was 0.08. The value of G2 was 26.3 into 10 raised to the power 9. The value of J2 was 4.97 into 10 raised to the power minus 9. So if you solve this, you're going to get T1 is equal to 0.224 T2. So that's an additional equation we have determined from the compatibility equation. I'm going to call this equation 1. So these T1 and T2 are basically the internal loads. Yes, this should be negative. Yes, thank you so much. And if you make a mistake, like don't put negative, then you're going to end up getting wrong results. So this is also super important to put the negative as well. So let's draw free body diagram again. This is TA, which is 160 Newton meter. And then you have reaction torques, which you have to calculate. That's the question. The question is, find out the reaction torques. But we cannot calculate the reaction torques this way because it's an indeterminate system. So, but we have an equation which gives us the relationship between internal torque T1 and internal torque T2. So what we can do is that we can make some cuts and expose T1 and T2. In this way, we'll have more equations, and then maybe we will be able to solve the reaction loads. So if you make a cut, I'm going to draw So if you make a cut and expose the internal load, this is how it looks like. So I'm going to do summation of moment along x-axis is equal to 0 or summation of torque is equal to 0. So from here, you're going to get negative TB, positive TB plus T1 is equal to 0. TB plus T1 is equal to 0. From here, you're going to get negative T1 plus 160 plus T2 is equal to 0. From here, you'll get negative T2 plus T1 is equal to 0. I'm going to call this equation 2. I'm going to call this equation 3. I'm going to call this equation 4. So now you have 4 equations and you have 4 unknowns. You have TB, TC, you have T1, T2. This is TC. So you have 4 equations, you have 4 unknowns. So you can calculate T1, T2, TB, TC. And in the question, you were asked to calculate TB and TC. So now I think you can calculate the reaction loads and also the internal loads. So let's try to solve this. If I put equation 1 in equation 3, then I can solve for one of the internal loads. So what is equation 3? Equation 3 is minus T1 plus 160 plus T2 is equal to 0. This is equation 3. What is equation 1? T1 is equal to negative 0.224 T2. This is equation 1. So if you put equation 1 here, you can solve for the T2. So it should be negative into minus 0.224 T2 plus 160 plus T2 is equal to 0. So from here, you can solve for the T2. So you're gonna get negative 130 roughly Newton meter. So that's the value of T2. Now you can use equation 1, which is T1 is equal to negative 0.224 T2. T2 we know is negative 130. So we can calculate for T2, which would be 29.3 Newton meter. So T1 is actually 29.3 Newton meter. So now we know T1 and T2, we know the internal loads. We can calculate the reaction loads. So if we use equation 2, TB plus T1 is equal to 0. So TB is negative T1, so negative 29.3 Newton meter. That's the answer for. And if we use equation 4, that is negative T2 plus TC is equal to 0. So we can calculate TC, which is T2, which is 130 Newton meter. So the answer for the part A is the reaction load TB is minus 29.3 Newton meter. The reaction load TC is minus 130 Newton meter. So that's how you can calculate the reaction loads and the internal load. So this was an indeterminate system, so that's why you couldn't do equilibrium equations alone. So that's why you have to like extract some compatibility equations and solve it this way. And I would say this is very important example with respect to the exam. So maybe you can go back and you can try to do it on your own, and you can practice 2 3 times. And also in the next lecture we'll do somewhat similar, one more example to make it more clear. But just gonna highlight like part 2 and part 3. So the part 2 is calculate angle of twist, right, at A. So angle of twist at A you can calculate by either T1 over G1 J1, or you can also calculate angle of twist by T2 L2 over G2 J2, because the angle of twist is same for the both. So you can calculate by either way. And you have all the values. We have already calculated T1, L1, G1, J1. So you can calculate angle of twist quite easily in this case. And the third part is calculate shear stress. So the formula for shear stress is TR over J. We already have all the variables. So we can also calculate the shear stress also for this case. And we'll talk